So let us now proceed to simple harmonic motion and uniform circular motion, or how will we link simple harmonic motion to uniform circular motion. Suppose we have a turntable here, okay, rotating at constant angular speed, and there is a ball attached to the rim of the turntable of radius A. Okay. So as the turntable rotates at constant angular speed, then the ball attached to it is moving around the circle at constant speed. Now, if an object that is moving around the circle at constant speed, we can say that that object is in uniform circular motion. Okay. And the turntable is hit by a light from the lamp, and the shadow will be projected here on the screen. There is shadow of the ball. While the ball is moving in uniform circular motion, then the shadow is moving in simple harmonic motion. So for better understanding, we will visualize that if this turntable is really moving by looking at this simulation. Okay. As you can see, the object that is attached to the rim is moving with the turntable. Okay. Assuming that the turntable is moving at the constant angular speed, then the ball attached to the turntable is moving in constant speed around the circle, so it is in uniform circular motion. While this object moving in simple harmonic motion, moving up and down at simple harmonic motion. Okay, so we will compare. Now, if we're going to view the turntable as the turntable rotating, so we will view the turntable at this position. So we can see that both balls are moving up and down. So it means the object that is moving in uniform circular motion is also moving in simple harmonic motion. Okay. So, but how can we determine the position, the velocity, and acceleration of an object moving in simple harmonic motion as function of time? We can obtain an expression for position, velocity, and acceleration of an object as function of time, moving in simple harmonic motion as by returning to the relationship between uniform circular motion and simple harmonic motion. So the first kinematic equation of an object moving in simple harmonic motion we need to determine is position. To determine the position x of an object in simple harmonic motion as a function of time t, let us focus first on the angular frequency. What is this angular frequency? By looking at this figure here, we will link the simple harmonic motion to uniform circular motion so that we can determine the position, velocity, and acceleration, or determine the equation of determine the kinematic equations for simple harmonic motion. So what is this angular frequency? This round object here is rotating at constant angular speed. So if this object rotating in constant angular speed, then the object around the circle is also moving in constant speed. So if this object moving in constant speed, so it means this object is in uniform circular motion. Speed is constant, but velocity is changing at every point of the circular path. Now, if the object attached to the spring is located at the amplitude, then the object moving in uniform circular motion will be located at this point of circular path. Now, if at this x position, then the object will be located at this position of the circular path. Now, if the object is at equilibrium position, the object that is attached to the spring, then the object will be located at this position. Now, if the object is at negative amplitude, then the object moving around the circle will be located at this point. The turning table is rotating at constant angular speed, so it will move a certain angular displacement theta. This is theta. So what will be the angular speed or the angular frequency? The angular frequency can be determined by the change of angular displacement over change of time. If the change of angular displacement is the final angular displacement minus the initial displacement, and the initial angular displacement is 0, then delta theta is equal to theta. And if delta t is final time minus initial time, and initial time equals 0, then delta t will be equal to t. So we will replace delta t by t. Or to find the equation of theta, then we have omega, theta is equal to the angular frequency omega times time. Now, if the object moves around the circle completely, then it means that it moves one cycle. And the time required to move one cycle is what we call period dt. And the one revolution is 2 pi, or that's 360 degrees. So this is one revolution, equivalent to one cycle displacement, over the time required to move one cycle, which is period. And period is reciprocal to the frequency. So you have t equals 1 over f. And then I will replace t by 1 over f. Then we have the angular frequency equals 2 pi times the frequency. So this f is the angular frequency, or the frequency. It means how many times this object attached to the spring moves from A to negative A and then back to A in 1 second. So this is how we express the angular frequency. That is equal to 2 pi times the frequency. Now, since the angular frequency is 2 pi f, and then also omega, the angular frequency can be expressed into the amount of angle displaced over time, and theta, or the amount of angle displaced, will be omega t. So we will replace omega t by 2 pi f, or the angular displacement will be 2 pi f t. So this is the angular displacement, 2 times pi f, the frequency, times now the position x as a function of time t. Okay. So again, if the object attached to the spring is located at the amplitude, then the object moving in uniform circular motion is located at this point of the circular path. But if the object is located here at x position, this object attached to the spring that is moving in simple harmonic motion is located at position x, then the object moving in uniform circular motion is located at this point of circular path. So this is the amount of angle displaced by the rotating, let's say, turntable. Okay, so from this position, that is the equilibrium position. From this point to that point, that is the displacement x made by the object attached to the spring from equilibrium position. Now, if we're going to get the cosine of this angle, or the amount of displaced, the angular displacement, the cosine of that, cosine theta, is the adjacent side, which is x, displacement from equilibrium position of this object moving in simple harmonic motion. So that is x over a. Now, to express the equation in x, or the position of this object moving in simple harmonic motion, then x here is the amplitude a,
cosine of angle theta. And what is this theta? That is 2 pi ft. So the position x equals a cosine 2 pi ft. Cosine ft. And then what will be the position of the object moving in simple harmonic motion? Position x ranging from A to negative A. The maximum displacement is A, either A or negative A from equilibrium position. Since cosine of angle ranges from 1 to negative 1, so 1, if the maximum is 1, then 1 times A will have A as the magnitude of displacement, or cosine of 2 pi ft is negative 1 times the amplitude, then we have a negative amplitude displacement.
So this is the displacement of an object moving in simple harmonic motion. It is expressed in as x equals the amplitude cosine of 2 pi times the frequency times time. X here is the position at time t, and x varies between positive A and negative A.
Now, the velocity v as a function of time t. Okay, so we will again use the reference circle, or we will link the simple harmonic motion to uniform circular motion, so that we can determine the velocity of an object moving in simple harmonic motion as a function of time t. Now, again, if this object is located at this point of the circular path, then the object moving in uniform circular motion will be located at x. Again, since this object is moving around the circle in uniform circular motion, so it has a constant speed, but velocity is changing at every point of circular path. So we have this, what we call the tangential speed, v sub t. The tangential speed or tangential velocity. Tangential velocity is always perpendicular to the radius of the circular path, and the radius of the circular path is equivalent to the amplitude of an object in simple harmonic motion. Now, the direction of the velocity of this object is always opposite to its displacement, direction of displacement. So if it goes to the positive displacement, then its velocity goes to negative direction, or always towards the equilibrium position. So this is negative Vx, right? Now, if this is angle theta, then this is also angle theta. So this is perpendicular, so 90 minus theta, this is the equivalent angle, then minus 90, so 180 minus theta, minus 90, that's also theta. Okay, the sum of interior angles of a right triangle, any triangle, is 180. So this is also theta. So this angle is opposite to negative Vx, or the speed of this object moving in simple harmonic motion. So again, why negative? It is opposite to the displacement, direction of displacement of this object moving in simple harmonic motion. So we have negative sine of that angle, theta. What is that sine of the angle theta? It's opposite side, which is negative Vx, over the hypotenuse side, which is the tangential velocity. Tangential velocity, it's tangent to the circular path. It only touches one point to the circular path, and it is perpendicular to the radius. So we have sine of theta equals the negative of horizontal velocity over tangential velocity. So we will express v of x in this equation. Negative vt, or the tangential velocity of an object moving in uniform circular motion times sine theta. The tangential velocity Vt is to be determined by the radius of the circular path times its angular frequency. And the radius of the circular path is equivalent to the amplitude of an object that is moving in simple harmonic motion. So R here can be replaced by A. So the tangential velocity will be A omega. So the tangential velocity here will be replaced by A omega. So we have Vt, Vx equals negative. Vt can be replaced by the amplitude times the angular frequency, or amplitude times angular frequency sine of theta. And what is this theta? Theta is 2 pi ft, which is equivalent to the angular displacement of this rotating object. So this is sine theta, or the speed or velocity of this object moving in uniform simple harmonic motion will be negative A omega sine of this theta 2 pi f t. Now sine theta is ranging from negative 1 to 1. Okay? The sine of any angle must be between negative 1 to 1. So the sine of angle theta is ranging from negative 1 to 1. Now, since the sine of an angle ranging from negative 1 to 1, then the maximum magnitude of the velocity can be determined. So sine of this sine 2 pi ft ranging from negative 1 to 1, then we have velocity equals negative A omega. So since we're looking for the magnitude of the velocity, then we can remove negative, or V equals A omega. So this is the maximum magnitude of velocity. Now, velocity varies in time. Depends on time, and it depends on position. The velocity at the amplitude is different from the velocity when the object in simple harmonic motion is at x position. And then at equilibrium position, it's different. It has a maximum velocity at x of 0 and zero velocity at the amplitude. Okay? And as well as negative A. Okay? Positions that are whose velocity are 0 are at A and then at negative A. The maximum velocity is located at the equilibrium position.
So this is the velocity v as a function of time t. As you look at the figure, there is tangential velocity, this point, tangent to the radius of the circular path of an object. And then v of x as the speed or velocity of an object in simple harmonic motion, which is opposite to the direction of displacement. So again, velocity is expressed in negative amplitude, omega sine omega t. So omega here is the angular frequency or angular speed. It should be expressed in radian per second. Since the sine of omega t ranging from negative 1 to 1, then the maximum magnitude of velocity is negative A or A omega.
So, this time we will determine the acceleration A as a function of time t of an object in simple harmonic motion. So let us link simple harmonic motion to uniform circular motion so that we can have the equation of the acceleration. Alright. Now, so again, this object moving around the circle is in uniform speed, or it is in uniform circular motion. Alright. Now, an object that is moving in uniform circular motion has acceleration because velocity changes. The tangential velocity changes. So it accelerates. But where is the direction, or what is the direction of the acceleration of an object moving in uniform circular motion? If you can still remember the topic of uniform circular motion, the direction of the acceleration of an object moving around a circle in constant speed is always towards the center, and that acceleration is what we call the centripetal acceleration, AOC. The centripetal acceleration. And AOC, or centripetal acceleration, is in this equation, expressed in this equation. AOC equals the square of the speed over R. Okay, over R. But the acceleration of this object moving in uniform simple harmonic motion always goes to the direction of the velocity of this object attached to the spring. So it has the same direction to the velocity of an object in simple harmonic motion. And AOC here is the centripetal acceleration of this object moving around the circle, and it is always towards the center of the circle. So if we're going to make a line here that is perpendicular to A, it points at that direction since the position, the displacement goes at that direction. These two quantities, the acceleration of this object and the acceleration, are in opposite direction. So that's why A is pointing at that direction. So if we're going to get the cosine of that angle, cosine theta, so if this is theta, this is also theta. Review on your geometry and trigonometry. So the cosine of that angle, cosine theta, is the adjacent side, which is A. A is the acceleration of this object moving in simple harmonic motion, over the hypotenuse side, which is equivalent to the centripetal acceleration. So we have AC, or the acceleration equals AC. Now, since the direction of the acceleration of this object is in opposite direction to the displacement, then I will mark this as negative A. So this is negative A, right? Or A as the acceleration of simple harmonic motion is negative AOC cosine theta. And what is this centripetal acceleration? It is the square of the speed over R. So we have A equals negative V squared over R cosine theta. And what is this R? The radius of the circular path, which is the same length of the amplitude of an object moving in uniform simple harmonic motion. So I will replace R by A. So A here equals negative V squared over the amplitude cosine theta. V is the maximum speed. What is the maximum speed? This is A, because the speed of this object is constant, which is R omega quantity squared cosine of theta over A. So again, I will replace R by A. So A here, the acceleration equals, write it here. So acceleration equals negative of A squared omega squared cosine theta over A. So I can cancel A and this one cancel. So the acceleration is A, negative A, omega squared cosine theta. So what is this theta? Theta is 2 pi ft. Then the acceleration of object in simple harmonic motion can be expressed into negative amplitude omega squared cosine of 2 pi ft. Okay, now since the cosine of 2 pi ft ranging from negative 1 to 1, or cosine of angle is ranging from negative 1 to 1, then the maximum acceleration can be expressed to amplitude times omega squared. So cosine, we will multiply it by 1, still A omega squared. So this is the maximum magnitude of acceleration. So this is the maximum magnitude of acceleration. Acceleration varies in time, so it's not constant. It changes at every position of an object moving in simple harmonic motion.
And this is the acceleration A as a function of time t. So by looking at this figure, there is an object moving around the circle in uniform circular motion, and its acceleration is towards the center of the circle, and it is expressed in A of c. And then the acceleration of an object in simple harmonic motion is opposite to the direction of the displacement. So as the object in simple harmonic motion moves at positive direction, then the A of x, or the acceleration, is towards the equilibrium position. So we get to have the cosine theta. Cosine theta here is A of x over A of c, which is the hypotenuse side of this right triangle. We form triangle out of this line, A of x and A of c. So we have the acceleration equals negative amplitude times the square of the angular speed or angular frequency, cosine of omega t. And this omega is 2 pi f, so we have cosine 2 pi ft. Since the cosine of the angle ranges from 1 to negative 1, then we have acceleration equals amplitude times omega squared. So we just multiply A, or amplitude, omega squared by 1 or negative 1. So this is the maximum magnitude of the acceleration.